Okay, you must develop your knowledge, your understanding, your intellectual capacities for becoming an independent thinker. And this is not so easy. And you need a lot of time and a lot of mathematics, but not only. So I am choosing some general subjects which allow me to slowly introduce new ideas. Okay? But your work must be independent, and you must read what is written in books. So please ask us to give you the right books, depending on your knowledge. Okay? We have spoken about mathematical models for describing physical phenomena in the last lecture. Now, I want to proceed giving you more details about this, and in order to proceed in describing you the philosophical ideas, I have decided to find a more specific subject, because this is very useful in your using computers. So I want to talk about discrete and continuous models in mechanics. We could change. Instead of mechanics, we could write physics, or we could write natural sciences. Okay, but because of your background, we will focus mainly on mechanics. Okay? In order to understand what is a mathematical model, let us try to make a drawing. I will show you some books where this drawing is more is better in appearance. I am not very good in drawing, so here you have the physical world. You have phenomena. In Greek, phenomenon means what is appearing to our understanding. Okay? So, phenomenon is the set of facts which we are observing. Okay? So, you see the moon, you see that the moon is sometimes big, sometimes smaller. This is what is appealing to our senses. These are phenomena. Here instead you have mathematical objects. Mathematical objects can be triangles of Euclidean geometry, could be equations, there is a relationship between mathematical objects and phenomena. To every mathematical object, you have a physical object which corresponds to it when you are building a mathematical model. So, for instance, you have a function which to every instant t associates the vector position for this, a vector which is the position of a material particle. This is a mathematical object. The phenomenon, the physical object which is corresponding to this mathematical object can be Earth. the Earth. And the mathematical object may be intended to forecast the motion of Earth around the Sun. Or it could be a bullet, you know, if you have a big cannon, the physical object could be the bullet which is leaving and then flying in the air and then landing somewhere. The equation of the motion as mathematical object is not the physical object. It is a model describing the phenomenon occurring to the physical object. Now, the mathematical objects here cannot describe everything which occurs in the reality. If you use the model material particle, your object is moving in space, so you are describing the motion. But you decide that the dimension of the physical body are not important in the motion you are studying. So you are conjecturing that it is not relevant in your modeling process what is happening to the shape of the moving object. This is an assumption which is not always verified. I tell you a nice story which explains you a lot, I think. I don't know if you like football or if you know about football. In Italy, we are crazy about football. Now, I was a student in physics department many years ago, and Maradona became the player of Napoli team. Okay. There is a phenomenon concerning the ball when kicked by Maradona. The trajectory of the ball kicked by Maradona is not planar. Maradona could kick the ball in such a way that the trajectory was not planar, while all other football players before Maradona, but also after Maradona, can kick the ball in such a way that the trajectory is planar. Now, let us use this phenomenon for understanding how it works, the activity of the mathematical physicist who wants to find the description of physical phenomena. If you assume you are a mathematician, you assume that F is equal mass times acceleration. Okay? And you consider as a force the weight, simply. It is very easy to prove that the trajectory governed by this equation must be a planar. The planar trajectory is characterized by the initial velocity of the material particle and by the direction of gravity acceleration. So, if you use the mechanics of material particle, then every trajectory under the weight must be planar. How it is possible that Maradona can kick the ball and the trajectory is not planar? If you don't make the distinction between the mathematical object and the phenomenon, you can say that Maradona is not existing, there is a God which goes there and moves the ball in a strange way, or similar magic explanations. Instead, in the spirit of Archimedes, what you have to say, I did some assumptions which are not verified. These assumptions are simplifying too much the phenomenon, and therefore I am not able to forecast what happens to my football ball. The professor of physics first year came to us and he told us, give me an explanation, a mathematical model, describing why the Maradona's ball is not traveling in a planar trajectory. It could be the object of a master thesis. It's not easy, but I tell you what happens. A ball is not an object without dimension. But this is not enough. A ball is deformed when you kick it. So, if you are very good and you kick it in such a way that it is not spherical anymore, you can have a spin of the ball which is deformed, and you can have an effect of friction, interaction between the fluid, air, and the ball, such that the resultant motion of the barycenter of the ball is not planar. So you need the theory of deformable bodies traveling in a viscous fluid with a deformation which is evolving in time, because the shape of the ball is changing during the trajectory. So the mathematical model here must include another function of time which gives you the angular velocity of the ball at every instant, and then you must introduce maybe 3 parameters telling you the 3 orthogonal radiuses of the ball, how they are deformed in time. So you need another 3 functions, Ri of t, where I is 1, 2, or 3. So you need to describe the physical system with more functions depending on time. And you must find the evolutionary equations for this set of equations, this set of kinematical descriptors. These equations have solutions in which x of t is not planar anymore. If you use COMSOL in a very wise way, you can predict the trajectory of the football ball kicked by Maradona. Why Maradona, in a sense, was a genius? He was a genius because he learned how to kick the ball without having a theory. And this is the reason for which you have only one Maradona. You have only one Maradona when something is not yet a scientific theory. If you have a scientific theory, you can build a robot, you write the equations inside the electronic brain of the robot, and he will kick the ball like Maradona and better than Maradona. Because you have a mathematical model describing what will happen, predicting perfectly what will happen. Of course, if instead of describing the motion of a ball in the air, you want to describe what happens to this ball when it bumps on the surface of water, then your model must become more complicated. Because you have two fluids, one fluid is denser than the other, the friction between the air and the ball and the water and the ball are different kinds of friction. Your model must become more and more complicated. So what happens? You have complex phenomena. Complex phenomena must be simplified. You cannot look, if you want to study what happens to the Earth in its movement around the Sun, is it relevant to know if in London it is raining? In the motion of the Earth around the Sun, the fact that in London it is raining or not is not relevant. So when you invent a mathematical model for describing physical phenomena, you must decide which part of reality is relevant and which part of reality is not relevant. You must conjecture the relevance of phenomena coupled with the phenomenon which is your main focus. So you must select. You must say this phenomenon is more relevant, this other phenomenon is more relevant. If you are a standard football player and if you are a goalkeeper and you know that Maradona is not playing against you, you can neglect the possibility that the ball is not following planar trajectories. You can use F equal ma for one barycenter of the ball and you are happy. If instead you know that you have Maradona against you, you must use a more complicated model, because your simplified model, you know, is not enough. This is the delicate game of the engineer. I try to explain you with another example. Let us talk about Navier. You know, Navier has been the inventor of famous equations for viscous fluid flow, Stokes-Navier equations. But he was also a big expert of solid mechanics. Actually, there is no true difference between fluid and solid mechanics. The theory on which solid and fluid mechanics are built are the same, is the same. We call it continuum mechanics. Okay. Now I tell you the story of Navier. Navier wanted to study what happens to a beam when it is loaded. He wanted to find a theory predicting the shapes of a beam when it is loaded. Look, this beam. It's very important to know that this beam is well behaving. You know, this city is not too much seismic. You know, in Italy we have a lot of earthquakes, but I think also in Iran you have earthquakes, right? Why this beam is not so big? Because you have another floor on the top, and because this building is in a second class region. The earthquakes here have a time of recurrence of 3,000 years, and the highest intensity of earthquakes expected here is 3.5 Richter. So this beam is big enough so that you can have more than 20 students in this room. Okay, so to know how a beam is deformed, it is a very important subject for practical applications. Do you know what Navier wanted to do? He introduced a set of atoms. He assumed that every atom was linked with a spring to the other atoms. Then he developed a very complicated averaging process and ended with some equations for the deformation of the beam. In this process, he made some mistakes and he forgot about Poisson ratio, in the sense that Poisson ratio in the theory of Navier has only one specific value, if I remember well, 1/4. Now, you take a specimen of a material, you pull it, and you measure easily another Poisson ratio. What do you think? Navier is wrong. Or you could decide that measuring other objects, if you believe in Navier as a god, you can decide that the other objects are not existing. It is up to you. Okay? Now let us think why Navier model was wrong. Do you really want to know where every atom is placed in this beam? Or you are happy to know what is happening to a section of this beam and to describe it with a more simplified model? If you remember Euler beam theory, in Euler beam theory you describe what happens to a beam assuming that every section remains planar and orthogonal to the average line. So you have what is called a simplified model. To be more precise, it's dangerous to include in your modeling too many details. At the end of the story is paralyzing you. Do you know how many atoms you have in an Avogadro number in a mole? it is 10 to the power 28. Okay? 23. Okay? It is an enormous amount of atoms. Do you want to follow all these atoms? You are happy to know something about the middle line of your beam, and in some assumptions, in some cases, you can assume that the section remains orthogonal. So, when you select a phenomenon, you must invent the mathematical model which is simultaneously complicated enough to describe the phenomenon in which you are interested, but simple enough to allow you to use the mathematical model in an effective way so that you can get solutions of your problems and you can predict the behavior of your system using your mathematical model. Okay? So this consideration now is very important when we talk about mechanics. To be too precise can be deadly. To be too rough can be also deadly. Because you want a precise prediction of the behavior of your system. Okay? So you must be good enough in choosing a model which is complicated enough to describe the phenomena in which you are interested, and simple enough to be usable, maniable, applicable to get prediction. Okay? This is not empty philosophy. This is a practical guidance to the action of an engineer. Because when you want to design something, you must be able to choose the right model which predicts what your physical object is doing. Okay. Now let's go ahead. Let us imagine that we have this beam here. We see at the top of our head. Okay. How do we want to model this beam? In history of science, you find mainly two different families, classes of models. There is Encke type model. You can model a beam like this. I explain you what we are doing. We assume to have rigid bars, pivots connecting two rigid bars, and a rotational spring which is connecting the two rigid bars. Or, so, let us think about this. This mathematical model, how many real numbers needs for describing completely the configuration of your system? The first bar is clamped, so its angle is fixed. Then you have the second bar. I need to know theta 1. the angle between the horizontal direction and the direction of the second bar. Then you have the third bar, and you have theta 2, and so on. So in order to know the shape of the beam using this Henke type, Henke is the name of the German engineer who discussed this beam theory, probably being one of the first, you need theta 1, theta 2, theta n, if you have n bars. We are assuming that each bar is rigid, so its length is not changing. This is an assumption which we can call inextensibility assumption. The bars are not extensible. So, what I'm telling you is that in this model, a finite number of real numbers is enough for describing the shape of the beam. This is what we call a discrete model for our physical object, which is the beam. Okay. Euler, instead, is not using a discrete finite number of parameters. Euler is introducing a curvilinear abscissa S along the axis of the beam, and for every S is introducing, let us consider the simplest case, a transverse displacement US. So it is telling that every point which is the barycenter of a section of your beam is displaced in the vertical direction, and this displacement has a component in this basis E1, E2. Along E2 it has the component US. So let us think a little bit. You plot the graph of US, which is a function, a real function of a real variable, and you get the shape of the beam. So every shape is given in terms of one function. How many functions do you have? One function for one shape. How many different shapes are possible? We must tell the properties of US. We are talking about mathematics. Is your beam allowed to break? We want to study phenomena in which the beam is not broken. So US is a continuous function. Okay. Do you want to allow to the tangent vector to the shape of the beam to jump? So do you want corners like that in your beam? This is a kind of damage. So we can assume that we are not good enough to study this kind of damage of the beam. So we can assume that US belongs to C1, the class of one-time differentiable functions being the derivative continuous. So the function and its derivative are continuous. Okay? Okay. How many C1 functions exist? Infinite. But how infinite is this infinity? I hope that you know that the polynomials of nth order are C1 functions. Okay, so there is a particular class which is very important in numerical analysis. If you consider A0 plus A1 s to the power 1 plus A2 s to the power 2 plus an s to the power n, this is a polynomial of nth order. This polynomial is a C1 shape, possible shape for your beam. So you have A0 is one parameter, A1 is another, A2, An. We have n parameters which are needed for characterizing a given polynomial. But n can be as large as you want. So, in order to characterize the functions C1, you may need an infinity of parameters. So while in discrete finite dimensional model for n-key beam, theta 1, theta 2, theta n with a given n is enough, if you consider the beam theory by Euler, no finite n is enough. You may need infinite number of parameters. I have given to you two elementary examples of a discrete model for a physical object and a continuous model, infinite dimensional model for the same physical object. The beam is always the same. We have invented two models. These two models are intended to describe the same physical object. However, one model requires a finite number of parameters, the other model requires an infinite number of numbers for characterizing every configuration of the system. Now, I'm using the words in a careful way. Here we talk about the state of the system. When I use the expression state of the system, I'm talking about the physical object. When I talk about the mathematical model, I talk about configuration. In the Persian tradition, there is exactly the same attention than in our tradition about the importance of words. When you use one word, the meaning of the word has to be very precise. The configuration of the beam using the model Henke is given by these n parameters. The configuration of the beam in the theory of Euler is given by the function us. The state of the beam is its physical shape. The state is always the same. Two different configurations are used for modeling the same state. Okay? You should never confuse the concept of state and the concept of configuration. The state cannot change. The configuration depends on the model you are using for describing the state. Okay? Okay, now we have a problem. Again, it is a philosophical problem, a practical problem. I claim it is the same. It is both philosophical and practical. By the way, I want, I'm sure that also in the Persian tradition there are the rules of rhetorics. Mahmoud, you tell me. The rules of rhetorics are taught to us by Demosthenes, who was a famous jurist and speaker of ancient classical Greece. The attention of a person cannot last more than 10-15 minutes. So if I'm talking more than 10 minutes, I must stop telling something which is lighter, okay, and then I must go back to the concept. Otherwise, I lose the contact. You must relax when I decide, not when you want to stop, because otherwise you could lose an important part of the discussion. Okay? Okay. Now, let us talk a little bit about the philosophy behind this. Why we want to use models? For describing, forecasting the behavior of this beam. Consider, you must be very wise if you will be engineers, or even wiser if you want to become a scientist. So when you decide which model you want to use, you must be very careful, because your model has to be precise enough to assure you that you know what will happen. Okay? So, how do I choose a model? To choose a model, I need to know which are the computational tools which I have in my hands. If you are born in France, 19th century, you don't have computers. Your computational tools are mathematical analysis and the solutions of the problems of mathematical analysis. So, let us imagine that we don't have computers, but we want to forecast the deformation of a beam. I hope that you will recognize the equation of Elastica. I will explain you the symbols. I don't know which symbols you are using. Km is bending stiffness. U is the transverse displacement. The primes are the derivatives with respect to S. This is the second derivative of Km, second derivative of U. Km can be a function of S because you can have the bending stiffness which is varying, okay? And this is the external applied force per unit line. Look at this equation. This is the magic equation of elastica. You know, Euler was writing in Latin. We have already spoken about the language. At the epoch of Euler, he was teaching in Berlin, St. Petersburg. The language of science was Latin. Elastica means in Latin a curve which is deforming in a way in which the deformation energy can be given back. There is no loss of energy in dissipation. Okay? Okay. Look at this equation. This is a very simple equation because you can solve this equation if I give you B of S. This is given. Okay? It is the externally applied force. If you don't know some of the details, after my lecture, you ask me and we organize something for giving you more details. I assume that everybody here knows the equation of elastica. But if not, don't worry, we will give you more details. And now follow the reasoning. US is the configuration of the beam. I need to forecast the shape of the beam, so I need to find U of S. In order to find U of S, the Euler theory tells me solve this ordinary differential equation. Solve the equation of elastica and you know which is the shape of your beam. Okay? So the conjecture made by Euler is every shape of the beam is forecast by solving this equation. Now, this equation is not so difficult because you calculate the primitive B, capital B of small b, and you get Km U second prime. Then you calculate the primitive of capital Bs and you get K U second. Then you divide. So the algorithm is very easy. I sketch it here. You know, I know exactly what Emilio is telling you and which kind of exercises you are doing in computational mechanics. I want to show you that Euler-Elastica equations are useful in a world where there are no computers. You are born now. We have powerful computers, but it is very recent. When I had your age, computers were a dream. Twin towers have been designed using the equation of elastica, making calculations with hands. Okay? So you must understand that the choice of one model or another one depends on your computational tools. And computational tools are changing quickly. Okay? So let us consider this. I take Km u second equal b, then I calculate the integral here and there, I get Km u second prime equal the primitive of b. Okay, I explicitly consider that I have an integration constant C0. Then I keep calculating primitives. At the end, what I get? I get 4 integration constants and all primitives one after the other of b. Okay? Then how do I get the integration constants? I need to tell how the beam is constrained. For instance, if it is clamped on the left, I have u0 equals 0, u prime 0 equals 0. Here I have no applied force, so I have Km u second prime equals 0, which is the boundary condition about shear stress on the free side, and I have Km u second equals 0 in L here, if the beam is long L. I'm sure that you have, even architects are obliged to do this calculation in one course. It is very basic, it is very easy. Okay? So, mathematical analysis is a computational tool which allows you to know, to forecast the shape of a beam using the model of Euler. For doing these calculations, you need to calculate the primitive of functions. And this is more or less what we are learning in calculus first and second year. Okay. Do you know that Eiffel was an engineer? Eiffel, using this theory, did manage to design the Tour Eiffel and the Statue of Liberty. This is a theoretical tool which is powerful enough to allow us to design complicated structures. But if you go in the basement of Ellis Island in New York, you will find some a big hole full of graphs, which are the calculations made by Eiffel for designing the Statue of Liberty. He needed a lot of handwriting calculations. Okay? But it is feasible. It is feasible. But now we have computers. So let me open a little bit a mathematical bracket, parenthesis. If I have x1, x2, xn, n unknowns, Okay? And I have a problem like this. A matrix A, n rows, n columns, applied to X, it means calculate the row times column product of A with X, equal B. So if you want, I can write it A11 X1 plus A12 X2 plus A1n Xn equal B1 and so on. AN1 X1 plus equal Bn. You have an abstract mathematical problem. This mathematical problem is look for the n real numbers x1, x2, xn such that replacing them in these n equations, they are all verified. Okay? This is the standard problem of linear algebra. Do you have ever heard about MATLAB? Yes? Do you know what it means, math? Matrix laboratory. MATLAB is the tool for solving these problems. You know, the use of articles is the tool. In Persian you have articles or you have declensions? Persian is a language with articles or with declensions? With articles. So you understand that I want to underline when I say this is the tool, it means the unique, the best, the most efficient. Okay? Okay. Now, if n is equal to 2, you can solve it by hand. If n is equal to 3, you can solve it by hands. But if n is 2 millions, you cannot solve it with calculations by hand using paper and pencil. Okay. Also, if it is 100, you cannot solve doing calculations by hand. So, if your problem is formulated in this way, find this solution. And if n is bigger than 5, you cannot do calculations by hands, and you are blocked. You must go back to Euler beam theory, to the equation of Elastica, because you need some time, but you manage to do the calculations. So why Henke type models, discrete ones, were invented in 1820 and then forgotten until few years ago? Because in order to have a reasonably detailed prediction of the shape of a beam, you need minimum 20 segments. So you need 20 angles, theta 1, theta 2, theta 3, theta n. You develop the model of Henke, I will tell you later how, and you get this equation. 20 equations, 20 unknown. You are blocked. You cannot calculate anything anymore. So, in 1981, when I was a student, they told me that the discrete models for mechanical systems are very nice, but totally useless in practice, because the continuum models are more practical. But when I was a student in 1981, the most powerful computer in Napoli, and Napoli is not a small city, and it is not a small university, the biggest computer in Napoli was occupying 2 floors of a building. It was a UNIVAC. In order to program this computer, I needed pieces of paper, cards, punching them, and for writing a code capable to find the first prime numbers in the first 1,000 natural numbers, I needed half a kilogram of paper, and the computer needed to work 2 hours, and I waited 1 week for getting the output. So you imagine that if I was wrong in typing one command, I needed to repeat it the week after. The computer in Napoli was 100,000 less powerful than my iPhone 6. Do you know what is happening? In history of humankind, we never had such a dramatic change in computational tools. The book written by Vincenzo Brunacci, the founder of mathematical analysis in Italy, in 1804, you know, Napoleon called him in Milan and said, "You must write the book of mathematical analysis for Italian engineers." He wrote 5 volumes. Okay. These books were used systematically in the same form for 100 years. Nothing happened in these 100 years. The time scale for scientific progress is dramatically changed. What we are teaching you, because I'm also teaching to my students about Elastica, is nowadays totally useless for practical purposes. Because we can solve a system of 2 million unknown in 15 seconds. The equation of Elastica is an historical dinosaur, which does not mean anything anymore in practical engineering. It has an historical relevance, it has a conceptual relevance, it is important for building your brain, it is very important for understanding mechanics, it has a cultural importance, but practical importance, 0. Nobody is using anymore, except in some very provincial places, is using now the equation of Elastica. Okay, now, how do we find this equation for Encke beam? It is very easy. you must introduce total potential energy. So every spring here has an energy which depends on the angle between the two bars, and then if you apply here a load, F, you have F times H. You know, you remember, I hope mgh is the potential energy of a point in a dead load force field. Okay, but here you have the force F. So this is external potential energy, and then you have internal potential energy, which is given by the variation of angles in the rotational springs. So you have potential energy which depends on theta 1, theta 2, theta n. Okay? You write your potential energy in console, it tells you where is the minimum. Why? Because equilibrium is attained in the minimum of potential energy. How do you find the minimum of a function? You calculate du over d theta 1. You impose it is equal to 0. And then you write du over d theta n, and you impose it is equal to 0. Now, if your energy is quadratic, you calculate the derivatives, you get a matrix, a linear problem like this. Okay? So, as Ivan Giorgio will show you, if you write Encke-type models, you can find in few seconds all the shapes, equilibrium shapes of a beam, using a very powerful computational tool. I want to show you, then we will show you the animations, the more details, but I will tell you on the blackboard. Because somebody could ask, all this philosophical discussion, is it useful? What I understand better and which kind of results I can get using this vision of science? Of course, I could tell you many things about many philosophers. I prefer to show you a practical example of difficult problem which I could solve using this vision of science, which is now published in good journals, and this solution, it is astonishing, nobody could find before. And you will discover this very strange. We did not believe that nobody had found the solution of beam elastica, which we have found before us, because we believed it is very easy. But after revisiting the problem with the new understanding, I hope I transmitted to you, you will agree with me that simply choosing the right point of view is 80% of the work to be done for solving a problem. Okay? By the way, the technicality, the reason for which I think that Ivan Giorgio is a genius is that I am telling him words, and out of these words he gets codes. So he's somebody who can talk with computers. Okay, I don't want to give you the impression that I am the typical full professor who is talking and then the slave are doing the job. I don't see. I have my left eye nearly blind and my right eye is 3/4/10. So I cannot write the code. But when I was young, I wrote many codes. So I can tell to even what one should do. Because the computer is changed, but structural programming is the same since the beginning of history of computers. The theory of how a code has to be written is always the same. Okay? Now I want to show you the problem. You have a beam. Imagine to have applied to this beam a continuous distributed constant force, like that. And I ask you which stable equilibrium shapes exist for this beam in large deformations. People studied this problem with the equations of elastica. Of course, these equations we wrote here are linear. They are valid for small deformations. So you need to formulate the equation of elastica in large deformations. Okay, in order to study very large deformation. Okay, one solution is this one. This is like a pending rope, a pending cable, more or less. Okay? However, using Henke discrete method, we have found this solution. When I've seen it, you know, I like very much go out with my bicycle. Do you have ever seen the wire of the brakes of the bicycle? They are sometimes doing this. So I started believing that this can be a solution, stable solution of the beam. Nobody believed it. We looked for this solution in every book, and we could not find it. We looked for in Scopus, and we never found it. If you use this discrete system and the total energy which I described to you before, this solution arises naturally after no more than 20 seconds of calculation. If you use elastica, you find it only if you know that it exists. Otherwise, you don't manage to find this solution in any way. Then I was invited in Helsinki to be the president of a PhD committee. More than a president, I was the opponent. In Finland, somebody wants to get a PhD must be opposed by an experienced scientist who tries to destroy his PhD. Of course, I will not drink the blood of any young people. I went there and I asked him politely some questions. Getting out of the lecture room, a colleague from Helsinki told me, look, I have in my lab a beam which resembles very much yours. Do we want to see if this solution is physically existing or not? We spent 4 hours between 6 to 10 in the afternoon, and I will show you the pictures. We got it. Nobody has seen it before, because nobody had the mathematical model forecasting its existence. This is very well known. I think it was Neptune, the planet which has been discovered because of its effect on the trajectory of the inner planets by Leverrier in 19th century, this planet was present in some pictures. Nobody has seen the white spot in that picture there, because nobody was expecting a planet there. Only if you have a theory which is telling you that you must look for something, then you find it. If you try to use Elastica to get this solution, you need hours of computation, even using discretization of the Elastica equation. Instead, if you use the directly discrete model of Encke type, you get it in few seconds. So we must go to a conclusion. We will go back to this discussion many times. When you want to solve a problem, what is a problem for engineers? To forecast the behavior of a certain physical system. You must focus on the phenomenology you are interested in. You must decide what is important, what is negligible, hoping that you are not wrong. Okay? Then you must formulate a mathematical model which is forecasting, in the sense that you solve problems. The solution of the problem is the prediction of the behavior of your system. And then at the end, you must compare your prediction with your measurements. Just one hint. Fluid mechanics is considered to be the most classical continuum model. You have a region where you have the flow, then in every point you have the velocity of the fluid, the density of the fluid. And you write equations. You want to solve these equations to know in every point which is the density and which is the velocity of the material particle of fluid traveling there. What is the material particle of a fluid? One could start to have doubts. Okay? So you can say continuum models are fluid mechanics. Fluid mechanics is continuum models. It's not true. there is a modern theory called molecular fluid dynamics. They imagine to have some balls here which are interacting one with the other, and they look for the barycenter of each ball during the time evolution. And with this model they get very effective predictions of the mechanical behavior of fluids. Once more, nobody knows which model has to be used a priori. Every problem requires that you stop, you think what you want to do, and in the gallery of available models you must pick the most appropriate one. So don't believe people telling you in structural mechanics Euler-Elastica equation is the final answer, or in fluid mechanics continuum models are the best one. You can never say. You must have your mind open and you must be ready to use the most appropriate model in the particular situation you are working. Okay? Okay, I hope that we are proceeding towards applications. Okay, next lecture will be more technical. Okay, thanks a lot.